Sounds good. And welcome, everyone, and thank you for the introduction. Today, I'm going to talk about Ventana Micro and how we are helping to bring RISC-V to the high-performance space in various data center, client, and automotive application areas. See if I can. Okay, there we go. So Balaji and myself are the co-founders of Ventana. We have both been working in the industry for a long time with many years of experience. Balaji has been a senior VP. He's been CEO of various business units and companies over the years, extensive experience there on the business side. Yet very technical. Myself, I have been designing and architecting high-performance processors and systems for over 35 years, including architecting the K6 family of processors that was acquired by AMD back in the 90s that got it back in the game competing against Intel. Later on, Balaji and I co-founded a startup called Veloce, where we approached ARM, which hadn't yet developed a 64-bit architecture, which is now called RVD23S. But we went to them, wanting to develop a 64-bit architecture and to bring ARM into the server space. And ultimately, that's what we helped do. We were the first architectural licensee of ARM. We work closely with them, and we actually had the first RVD23 high-performance implementation, even ahead of ARM's internal CPU teams. And so along the way, we learned a lot, and through that whole journey of working to bring ARM V8 into the server space. And we are now bringing a lot of that experience into doing the same for RISC-V, to bring it not only into the data center market segments, but into other market segments where high performance matters a lot, both say, in terms of client devices as well as automotive, and also in terms of edge AI as well. So, in short, we have both ourselves and our team is a very experienced team in developing these kind of high-performance processors and system designs. Ventana, from the very beginning, has been very actively involved in RISC-V International itself to help foster and lead the development of the architecture as well as software efforts and so on. You can see some of the key roles that myself and a number of others from Ventana play within RISC-V International. And so it's been a key thing for us, is both driving high performance RISC-V, also helping drive and further develop RISC-V architecture. And then thirdly is also to help drive the development and maturing of the RISC-V software ecosystem. And one important part of that, or actually let me go back a step, that today, as I'll talk about a little bit later, there's a lot of applications, a lot of software that already runs on RISC-V. And again, I'll talk about that later. But still, there's more work to be done to both more fully mature the RISC-V software ecosystem, as well as to also optimize the software best for RISC-V. And that's part of what motivated the creation that was recently announced of RISE, which stands for RISC-V Software Ecosystem. Its goal is to accelerate the development of open source software for RISC-V, raise the quality of all those implementations, and to really aggressively push forward the RISC-V software ecosystem by bringing together a lot of key companies both large and small, such as Ventana, and you can see the names on the bottom of the slide of some of the key founding members. And then there are further members that are also joining RISE as well. And together, in a typical open source fashion, we can all contribute resources to work on further developing and maturing the software ecosystem. And as part of the power of RISC-V is that it's not an architecture owned by one company like an ARM or an Intel, but that you get the power of many companies coming together, contributing to develop the architecture and the software. As far as Ventana itself, we're one of the early people to focus on high performance RISC-V, as well as the idea of chiplets. And I'll talk about both of those a little more on later slides. But as part of all that, we've brought together one of the best CPU teams in the world. A lot of us that we've worked together in the past, past designs, past architectures, a lot of accumulated experience of how to do things right and what not to do. As I'll also talk about, we have our first generation products that we've introduced, and we have a roadmap to following generations. I'll also talk about chiplets and how that's a key thing that we've also been pursuing as part of what we offer to our customers. I'll also talk about the key market segments that we're focused on, which includes the infrastructure side of data center, as well as the mobile and automotive segments. And I've already talked about RISE and a lot of the ways that we actively participate and contribute to RISC-V International. There's four key pillars to what is special about what we do. The first is we are doing high performance, true high performance RISC-V design, which means both high single thread performance as well as high socket level performance. When you have a lot of cores together in a socket, and that you have very power efficient and high scalability to high core counts, as well as simply having high single thread performance. What we developed is also very portable across process nodes. And that affected how we developed the microarchitecture and so on to make it easy for our design to port across different generations of process as well as different boundaries. Second is a big focus on enabling chiplets so that you can take what used to be monolithic silicon that takes several years and $100 to $200 million to develop an SoC and take it into production, to now be able to disaggregate that silicon into chiplets that can be, their development can be decoupled and done in parallel. We can focus at Ventana on the high performance compute chiplet, which is one of the more challenging chiplets, and enable our customers to then develop their products, their SoCs, using our compute chiplets in a much shorter time frame and for a lot less money. We also, like I mentioned, are one of the founding members of RISE, and we do a lot of stuff on the software side of the ecosystem, not just simply developing high-performance compute IP and chiplets. And another thing that's a key part of what we do is leveraging the flexibility that RISC-V allows in terms of extending the architecture and supporting domain-specific acceleration. Okay, last December at the RISC-V Summit in California, we introduced our first generation product, the Veyron V1. This shows, in terms of socket level performance, a comparison against Intel and AMD and Amazon AWS, the Graviton 3, where at a socket level for comparable power budget, or TDP, we both have high performance per core, but also very power efficient cores, so that we can also pack more cores into a packaged part within a given power envelope. And so that gives us, that aggregate, the per socket performance that's much better than what others are able to offer. And again, I'll talk some more in a bit about chiplets, which has been a big focus of ours from the beginning, and something that has a lot of attractions to most of our customers. But first, I just wanted to note that traditionally in the industry, people developed a large monolithic SoCs. Semiconductors has really been a foundation of a lot of the modern economy, and there's been this unrelenting development in process technology, but also in terms of then consolidation among semiconductor vendors. Along the way, that also has led to a dual monopoly between x86 and ARM. And with the complexity of the products, the time to develop products has grown. At the same time, there's less competition, that there's a limited number of silicon vendors that customers, that OEMs can look to get silicon. And increasingly nowadays, OEMs are looking not just for silicon, but silicon that enables differentiation and innovation, so that a customer can have silicon that's optimized for his applications, versus simply having to accept what is available from a silicon vendor. Yet, for an OEM to have that control over the silicon that they want that's optimum for their applications, to do it themselves is a very high development cost, requires a lot of expertise. And so the question is, how do we address this dilemma, this problem? And that's where chiplets comes into play. On the left-hand side, as you have sort of the past and up to today, people doing monolithic SoCs, takes lots of time, lots of money. You have to anticipate 2-3 years in advance what is the right product features for that product, and hopefully you get it right. And you'll find out 2-3 years later. And oftentimes, it's not quite right. And you've spent a lot of time and money. As you then transition to a chiplet-based architecture, where Ventana, we focus on doing sort of the challenging high-performance compute chiplets in a leading-edge process node, while a customer can either develop himself, or he can get from someone else what we call an I/O hub that can be done in a cheaper process node that isn't leading edge, and that customer can incorporate their special IP into that hub, and/or they may have their own domain-specific accelerators that they also want to hook to the hub, so that between the hub and the various chiplets that they choose to combine together into a product, they can create a solution that's optimum for their application, and do it in much faster and with less cost. This summarizes the key market segments that we are addressing. Automotive has been a big area that's come on strong over the past year. There's a lot of architecture changes happening in automotive, a shift towards a need for much higher performance for both ADAS, infotainment, telemetry, etc. I'll talk more about this on a later slide. And then in the data center, on what we would call the infrastructure side versus the customer-facing side of data centers. Half of the data center now is the internal infrastructure for storage, for networking, for load balancing, for a wide range of applications. Those are relatively contained software stacks that a hyperscale data center company they control, and they're able to move fairly readily to a new architecture. Client and mobile has also been a big area that's come on strong over the past year as well. Both in automotive, data center, and client, there's many companies that are strategically recognizing the value and the need to evolve to RISC-V based products. And then certainly compute at the edge, especially with generative AI, is also becoming an important area for us that we are addressing as well. As a company, we offer what we develop in two forms: as IP, both CPU and a cluster of CPUs and cache hierarchy and so on, that a customer can integrate into a monolithic SoC if that's what makes sense for them economically. If they are doing something for a very large, high volume, large scale. For many of our customers, what makes more sense economically now is chiplets. And that's where we provide compute chiplets. We also provide a complete die-to-die solution to enable customers to then create these multi-chiplet types of system design. And this is an example more, say, in a server application where there's a ready ability to scale from maybe a lower end server design with, say, 2 Ventana compute chiplets up to a high-end server design with a far higher core count, utilizing more Ventana compute chiplets. And this is true in other areas as well as server, where a customer, based on his application needs, he can decide, well, how much compute does he need? How many chiplets he wants to attach, for example. One key thing to enable chiplets and the disaggregation of monolithic silicon is to have a die-to-die solution that is very power efficient, small area, supports high data rates. We help develop and drive what is now the BOW standard under ODSA, which was developed within OCP. And we are now also very much involved with doing similar with UCIe. And part of that is not just at a physical layer, where you have BOW and now UCIe has appeared more recently. We have developed a complete die-to-die solution, which is not just physical layer, but also the controller, the link layer and transaction layer. And that is based on a very streamlined transaction layer and link layer, so that we can achieve very low latency as well as the power efficiency. So that even though you're disaggregating monolithic silicon into multiple chiplets, latency-wise and performance-wise, it seems almost the same as if it was monolithic silicon. That the die-to-die links are, largely transparent from a performance and latency perspective. In automotive, there's a lot of big transitions happening from today's domain architecture to more of a zonal architecture, and with that comes an increasing need for centralized high-performance compute. Basically, you now have not just one but multiple servers within a car. Part of this also is a major change in the software environment from lots of little localized microcontrollers to a more unified software environment that is really sort of a software-defined vehicle, and so these sort of server class compute abilities and chiplets helps support development of silicon products for this new zonal architecture within automotive. And this is sort of one example of where you may have an automotive-oriented hub as chiplet, as we would call it, to which one could attach one or more Ventana chiplets. You may have maybe some, for example, integrated AI acceleration in your base I/O hub, and then you can add on more chiplets for higher end designs. You may want to add on GPU. Integrated in the hub, you may have a lot of typical peripherals and I/O interfaces that you want for automotive. But part of the point of this is that you have a modularity so that one can develop multiple products from low end to high end versus having to do complete new chip designs for different market segments that an auto company may address. This slide, helps address many companies when they start talking with us. A common question is, well, what about software for RISC-V? Isn't that still a work in progress? And in fact, our message is, well, no, actually, there's a lot of open source software that is running today on RISC-V. Everything shown here, these various software stacks, within storage, networking, security, etc. We've ported all these onto RISC-V, and we're able to show demos to our customers of each of these software stacks running on Ventana CPUs and on RISC-V, and that is all available today in terms of all these software stacks running on RISC-V. In closing, that Ventana, we set out to bring RISC-V to high performance market segments, and we've started that with our first generation Veyron V1, and we're actively already well into working on our second generation. And again, the focus is on initially it was the infrastructure side of hyperscale data center, as well as high-end embedded. Certainly over the past year, automotive and the mobile/client spaces have come on very strong in looking to start moving to RISC-V. And between what we've been doing, starting from several years ago, in terms of high performance, in terms of chiplets and enabling chiplet-based designs, that we're in a strong and unique position to help bring RISC-V to high performance in these various market segments. And that is it. I can open up for questions.
Thank you. You still have 7 minutes or more. But anyway, this is the kind of closing, right?
Yes,
okay.
Yes. I did want to try and allow for some time for questions.
Okay.
Versus taking up all the time with just my presentation.
Okay. Okay.
Certainly, I can go back to any slides that people might want to hear some more about as well.
Let me ask the audience if they have any questions, comments first. So, ご質問、コメントありますか？ぜひお願いします。じゃあ、私はまた、はい。林さん、はい、どうぞ。あちらの方。There are one guy going to ask a question to you.
Thank you, Greg. So it's a great presentation. Could you show us the performance comparison graph? Spec into number.
Show what again?
You show the performance comparison graph. It's very impressive number. So is this a result of real system or simulation or something?
Okay. So on the one hand, we will be sampling to our key customers by the end of this year. In the meantime, of course, we've done simulations, but more than that, we also enable some of our early customers to be able to port software and run applications and benchmarks on our design based on an FPGA prototyping platform, so that in advance of having putting silicon in their hands later this year, that again they can be not just like simply us doing simulations, but through this FPGA prototyping platform, customers can go do their own evaluations. They can start porting software. They can start running a variety of software, not quite as fast as real silicon, but it's the real design.
Okay, thank you very much. Yeah. Anyway, this is very impressive. Thank you very much.
Oh, thank you.
So, any other questions? Yeah, okay. どうぞ。2列目の方。There are one more guy ask a questions.
日本語でもいいですか？
ちょっとやれればいいですよ。どうぞ。簡単な質問にお願いします。
質問は簡単なんですけど、多分17ページ。
So, would you show us the page 17?
Tell me which one?
I know.
Page 17. 17.
OK。ソフトウェアで Linux が Debian と Ubuntu しか書いてないんですけども、データセンターでは Red Hat 必須なんですが、ないんですかと。それから、Kubernetes が入ってないんですけど。
ちょっと待って。The first question is that this slide shows, in terms of Linux distribution, only shows Ubuntu and なんだっけ見えないよ。But the guys thinks for the data center applications, Red Hat support is mandatory, kind of. So why Red Hat doesn't not included there? So
yes, a good question. So on the one hand, Red Hat tends not to be the most aggressive in terms of supporting a new architecture. And so that's why some of the other Linux distros support RISC-V sooner than Red Hat. Now, at the same time, Red Hat is one of the founding members of RISE. And so I think that very much signifies that Red Hat is becoming very serious about supporting RISC-V. And so it's just a matter of not much time, to see them, start seeing maybe a support from Red Hat. I can't speak to when they would have product introductions, but the fact that they are a founding member of RISE says a lot. Whereas on this slide, this slide was true even last year in terms of where the state of software on RISC-V was already at, and now it's based on some of these other Linux distros. Hopefully that answered your question.
最初の部分しか覚えてないんですけど、最初の部分はレッドハットは要するにRISC-Vのサポートをあまり積極的でないと、遅いと。で、なんかレッドハットは他の団体になんかライズとかなんとか言ってましたに中心メンバーらしくて、あまりそのRISC-Vをその積極的に使う態度じゃないので、まだ入ってない、入れてない、そういう質問書いて。So why Kubernetes isn't included there?
Yes. I think the short answer is that this set of software stacks is what we had first focused on all bringing onto RISC-V. And like I mentioned, this is all in place last year. We continue to work to bring other open source software applications onto RISC-V. And I don't remember offhand if Kubernetes is already supported on RISC-V yet, but that's one of a number of things that are in the process of coming to RISC-V. And like I mentioned earlier, Ventana was one of the early people to really focus on bringing a lot of this open source software under RISC-V. And now with the creation of RISE, that this really brings together a lot of companies to continue that work. So I don't remember the status of Kubernetes offhand, but there's a lot more coming to RISC-V soon, past what's mentioned on this slide.
要するにこのスライドは最新のもので、最新の状況はわからないというのが、簡単に言うとそういうふうです。でもRISC-Vに来ると思うよと言ってましたけど。はい。他にご質問、Any other questions? まだ時間あるのかな ?20 分。まだあります。じゃあ僕一つ聞きたいんですけど。May I ask a question from me? I'm a moderator.
Oh, yes.
Okay. So I understand, so your company is kind of try to use advanced chiplet technology. But as you know, so AMD EPIC uses chiplet, and even Apple use die-to-die connection for high-end Mac Pro chip like M1 Pro or M2 Pro. So I understand their chiplet is chiplet, of course, but kind of customized chiplet, no standardization there. So but in your solution, so I heard there are many, standardization effort or proposal for chiplet, but as my understanding, so none of them is really materialized yet. So would you comment on the standardization of chiplet, or are you okay with yet another customized version of chiplet? That is my question.
Okay, no, thank you. That's a good question. So, certainly chiplets is relatively new to the industry, and like anything new, it goes through an evolution in terms of all the support to enable chiplets, falling into place within the industry. And you, of course, have some early adopters, like you mentioned, AMD, for example, and Apple. And we also very early on recognized the value of chiplets and what that enables, both technically, engineering-wise, and economically. Early on, you start off, there's no standards. And so that's why the first key focus was to establish a physical layer standards. And so that's where we helped drive the development of the BOW, or a bunch of wires standard, which is a form of die-to-die parallel interface done under ODSA, under OCP. And then, like I mentioned earlier, more recently, UCIe was introduced, and we're also working closely with maturing UCIe. There's a new 1.1 version of the spec coming soon. And so that's at a physical layer in terms of establishing standards. The next level is up to the link layer and eventually transaction layer. And early on, we developed a complete die-to-die solution, including sort of the link layer and transaction layer. And then we've actually offered and worked with ODSA to establish some link layer standards as well. In fact, that has also happened earlier this year. based on all our link layer architecture. And so again, we're starting to get some standardization at that level. But ultimately, what you want to have is when people are disaggregating monolithic silicon, they're starting with, within that silicon, they're typically using, AMBA bus standards like CHI and AXI and other variants. And you want to continue to use those as they evolve or migrate to a chiplet-based design where they are disaggregating that monolithic silicon into multiple chiplets. And so in contrast to, for example, using UCIe, I meant to say, in contrast to, say, using CXL or PCIe, or as you noted, like say AMD has their own proprietary, protocols for doing die-to-die. That we're working to drive, fuller standardization based on AMBA bus protocols like CHI and AXI and others, so that people can continue to use what they're used to working with inside silicon, and to continue to use those protocols even between chiplets. And so that's the die-to-die controller stuff that we've developed that enables that, so that you have protocol standards, the popular AMBA bus standards, and then you have physical layer standards, and then controller IP that can go between those two. And certainly this is a developing thing like any new technology area. We've done a lot of work early on in terms of being able to provide a complete die-to-die solution to our customers, and we're also working to increase standardization at various levels, and that's will continue to be true over the next year or two, so that there's increasingly more and more standardization, and eventually you can get to the point of really being readily able to mix and match chiplets. Today, we can enable that with customers within a more contained ecosystem of partners, but we certainly are driving towards this more open market of being able to mix and match chiplets in the future. Did that address all of your questions?
Yes, I think so. So in short, my feeling is your plan is kind of go with your customized chiplets, in short. This is my impression. Am I wrong?
Well, yes and no.
Yes and no.
Let me go back to this slide. That we find that for many customers nowadays, what makes more economic sense is to move to chiplet-based design. It gives you a lot of flexibility and modularity, and enables you to kind of customize a product with the right combination of chiplets and features, and to do that much faster and for less money. And so we offer what we developed in the form of a compute chiplet that in our first generation can contain up to 16 cores, as well as a cache hierarchy and a coherent fabric. But there are some customers that, especially when you're at larger scale in terms of volume, where it economically still makes sense to do monolithic integrated silicon. And for those customers where getting an IP offering from us makes more sense, we also support that as well. So basically we support both models. It depends on which one makes more sense for each of our customers.
Okay, yeah. So time is up. So sorry. So thank you very much for Mr. Greg Feyber. So let's close the session. So thank you very much.
Yeah, thank you.